Hello everyone, welcome to the second class of this week. You've seen the last week what we discussed is in any engineering design, selection of material is the important step, and selection of a material for a particular design which is subjected to particular environment. The selection depends on the comprehensive understanding of a material or rather how a material behave when it is subjected to certain kind of environment, a certain kind of agitation, a certain kind of threat. So, understanding of that response is very important. Now, when a material is subjected to any kind of threat like human being, it also becomes stressed, right. This is one way of responding to that threat. Now, in addition to that stress, there is another kind of response which is strain, which is measurable, which we can visualize, unlike stress. And then what we were discussing in this week is how to define this stress, how to define strain, how to represent them. And then the discussion we started the last week is the concept of stress. We started with the definition of definition that we had in our school days, that stress is equal to force by area. But then we discussed we have to look beyond this definition, and because now we are not dealing with just one area or one force, there are different areas, different planes and different forces we have. So, there are different components of stress. We also discussed that the stress is a point-wise description of the response of a body. We cannot say that stress in a body is this. These statements is vague in the sense that stress may be uniform, may not be uniform. So, the correct statement will be stress at a point in a given body, and then so stress is a point-wise description. Then we also discussed that a point can be idealized by an area or a volume depending on the dimension we are dealing with, the infinitesimal area or infinitesimal volume. And then what we discussed today is we'll start with fixing our coordinate system and the sign convention, and then we'll see what are the different stress components we have at a point and how to represent those stress components through a schematic diagram. And then we also see that some of the properties of this this stress at a point. Okay. Now, so today's topic is the stress as a tensor. We'll see that you have a brief description on tensor in the very first week of this course. Okay, you see what we have done so far is, suppose we have any arbitrary any arbitrary body. Suppose a body like this, okay, any arbitrary body, take slightly bigger, any arbitrary body, and in that arbitrary body, suppose we have a point here, any point at this point, okay. Now, around this point we can have a small an infinitesimal area like this, and then this is the representation of this area is the representation of this area is the representation of this point. Okay. So, now the stress, there are different components of stresses. So, stress at this point we can show graphically or schematically through this diagram. Okay. Now, let us first fix our sign convention. The sign convention that we use is, this is the coordinate system, this is x, this is y, and if it is in 3D, then we have a z axis as we will be using right hand thumb rule for this coordinate system. Okay. Now, once we have this coordinate system, we have to fix the sign convention for this stress. We have, if it is tension, we take tension as positive, okay, and compression as negative. Compression is negative. Now, you put a star mark here because we will see that in addition to compression and tension, there is one more deformation mode. We will not discuss that right now. Next class, when we discuss about strain, then we will come to this point once again. Okay. Now, you see, we also discussed last week that if we have a plane, if we have any arbitrary plane, if you recall, if you have any arbitrary plane, then on this plane we can have a normal component of stress, and we also have a tangential component of stress. So, this is normal component and this is shear component. Okay. Now, let us see then. Now, if this is a point in 2 dimension and this is the representation of the point, on this diagram we will represent the force stresses. So, on this we have a stress component, and on this surface also we have stress component, is a normal stress component. Okay. Now, since this direction is x direction, we call it sigma xx. This is sigma xx. Now, what this double x means will come shortly. Now, then on this direction we have a normal stress, this is normal stress sigma y. On this also we have a normal stress which is sigma y. Okay. So, these are the normal stresses we have. As tension is positive as per our sign convention, the tension positive means the forces will be in this direction along this in x direction, and the force will be along this in y direction. Okay. So, the normal stress will cause elongation in the body in that particular direction. That is the sign convention here. Now, then we have shear component. Now, shear we have sign convention is this. Now, we have this is a shear component, and this shear component, let us write it as sigma x. This is sigma x y. Okay. Now, again I will come to this point why it is sigma xx, what is the meaning of sigma xy and so on. And then we have here also we have the same sigma xy. On this plane we have another shear component which is sigma yx, and on this plane also we have a shear component which is sigma yx. Okay. Now, what is sigma xx and sigma yy means, sigma xy means? You see, this is the let us draw this is the x direction and this is the y direction, right? This is the y direction. Now, sigma xx, it is acting on this plane, right? It is acting on a plane which is normal to x direction. So, this first x stands for the plane on which this stress is acting. Okay. So, this x means that it is acting on a plane which is normal to x direction, and then the second x here is okay. It is acting on the plane, but on that plane what is the direction of the stress? On this plane the direction of the stress is x. Okay. That is why this is sigma xx. Now, what is sigma yy? First y defines the on which plane the stress is acting. For instance, this is acting on this plane which is normal to y direction. So, this first y stands for that. And then the second y is on this plane, the stress is in the y direction. So, this is sigma yy. Now, why it is sigma xy? Because the first x, as I just now said, it tells you on which plane it is acting. It is acting on a plane, it is acting on this plane. So, it is acting on a plane which is normal to x direction. That is, so the first one is x. And then on this plane, in which direction this, what is the direction of the stress? Direction of the stress is sigma y. So, similarly, this is sigma xy, and you see this is sigma yx. And why it is sigma yx? Because the first one is y, which is acting on a, which is the plane on which it is acting. It is perpendicular to y direction, and on this plane it is acting in x direction. It is acting in x direction. That is why it is sigma yx. Okay. There is, we'll see shortly that the sigma xy, sigma xy is equal to sigma yx. Okay. But just bear with me for some time to come to this point. Okay. So, this is the representation of stress at this point. Okay. Now, this is a schematic representation of the stress. So, how many stress components we have now at this point? So, we have two normal stresses. we have two normal stresses which are sigma x and sigma y. There are two normal stresses and then two shear stresses sigma x y and sigma y x. Okay. Now, so these are the four stresses we have. So we can represent this. See, this is the graphical representation of the stress at that particular point, and this is the same stress written in a vector form. Okay. Now, another way this stress can be represented, and this representation is, say, tensor representation sigma xx and then sigma xy, sigma yx and sigma yy. This is okay. Now, the diagonal term it is written in terms of matrix. Okay. Now, sigma the diagonal term of this matrix are the normal stresses sigma xx and sigma yy, and then the off diagonal terms are the shear stresses. Okay. Now, so this is sigma. So, this is the graphical representation of the stress at a point. This is all the stress components written in vector form, and then this stress component written in a matrix form, in a tensor form. Okay. Now, these are the stress components at a point in two dimensional space. Now, coming to this quickly at this point, you see, now we all are aware of equilibrium equation, right? Equilibrium equation says that the body has to be the body is in equilibrium, then every point in the body is in equilibrium. Every point in the body is in equilibrium means static equilibrium, means that the summation of forces in all directions should be equal to 0, and the summation of moments about any point should be equal to 0. Now, this body has to be in equilibrium, and this point also has to be in equilibrium, and these are the stresses at this point. Let us see whether this stress, the distribution of stresses and the different components, they satisfy the equilibrium condition or not. Suppose the distance, this distance is dx and this distance is dy. Dx and dy you do not have to write when you represent this stress at a point in a graphical form. Dx and dy required to convert these stresses to forces, right. Now, so equilibrium conditions, the first equilibrium condition says that summation of forces, summation of force in x direction is equal to 0. Let us see whether it is 0 or not. The summation of force, this plane, the length of this plane is dy, and sigma xx is the normal stress on this. So, sigma xx into dy, we can assume it is unique thickness. Okay, sigma xx, and then minus, this is in the negative, in the other direction, sigma xx into dy, which is equal to 0. So, summation of fx is equal to 0. Similar way, you can show that summation of y, that is also 0. Now, no, sorry, there is one more thing. Now, this is another two forces we have. One is this force in this direction and this force in this direction. So, sigma yx, this is acting on delta x minus and then plus sigma yx, which is acting on delta x. So, that is equal to 0. So, summation of fx is equal to 0. Similarly, you can show that summation of fy is equal to 0. Okay. Now, we need to let us see whether the summation of moment is equal to 0 or not. Now, if this point is O, if I take moment, summation of moment about O, and equilibrium condition says that has to be equal to 0. So, let us see if this is O, then these normal stresses will not cause will not contribute, because this moment is taken from this point, the center point, and this normal stress multiplied by this area the force in x direction will pass through this center point, Therefore, this normal stress will not contribute to this equilibrium equation, only the shear stresses will contribute to this equilibrium equation. Now, you see, now sigma xy, this one, and sigma xy, this sigma xy will produce an anti-clockwise couple, okay, and this anti-clockwise couple is sigma xy. This is the stress, and then this is acting on dy. So, multiplied by dy, which becomes force, and then multiplied by the distance between these two forces, which is dx, this becomes an clockwise couple. Now, similarly, an anti-clockwise couple. Similarly, a clockwise couple will be created by sigma yx, right. This is also sigma yx acting on dx, and the distance between these two forces dy. So, they has to be equal to 0. So, this becomes, you check, sigma xy is equal to sigma yx, right. Just now, that is the thing we wrote here. So, this comes directly from the moment balance equation, right. So, if sigma xy is equal to sigma yx, then this representation, this is a vector representation, it essentially becomes, this becomes 1. So, we have just 3 component of stresses, sigma xx, sigma yy, and one shear stress, either you can write sigma xy or sigma yx. And then in a tensor, in this representation, this is diagonal, which are the normal stresses, and the off diagonal, which is the shear stresses. Now, we have seen that the off diagonal terms are same. So, this matrix become symmetric matrix. So, this is a symmetric matrix. Okay. This is symmetric. So, this is the representation of stress in 2 dimension. The same thing we can do in higher dimension. If you recall that if it is higher dimension, then any material point is now in the 2 dimension, it was just a square, and in this case, or rectangular. In this case, this representation is in 3 dimensions. So, we have 3 planes on this. Okay. So, now if it is in 3D, this is the diagram. We write our coordinate axis. Coordinate axis is just now we showed. This is okay. Let us use a different color for this. Okay. So, coordinate axis is, this is our x, this is y, this is x direction, this is y direction, and this is our z direction. Okay. Now, so let us show these traces on this plane first. Now, on this plane, we have one normal stress. One normal stress is, this is sigma xx. Why it is sigma xx? Because it is acting on a plane which is perpendicular to x axis, and then in the direction of x. So, sigma xx, right. And then we have one more stress, a tangential stress, this is sigma xy, Why it is again sigma xy? It is acting on a plane perpendicular to x axis, and the direction of the stress is y, in the y direction. And then we have another stress component like this. This is sigma xz. So, this is acting on a plane perpendicular to x direction, and the direction of the stress is in z direction. So, this is on a plane which is perpendicular to x direction. Let us do it for other plane. So, on this plane we have first a normal stress. Normal stress is sigma yy, and then we have one shear stress which is sigma yx, and then another shear stress we have this one which is sigma yz. Sigma yz, it is acting on a plane on the normal perpendicular normal to the z axis, normal to the y axis, and the direction of the stress is in the z direction. Now, then on another force, on this plane we have a normal stress which is sigma zz. Then we have a shear stress like this which is sigma zy, and then we have a shear stress like this, which is sigma zx. Okay. Now, similarly, so for clarity, these stresses are shown only on this plane. Other 3 planes also we can have similar kind of stresses. Now, only thing is that your sign convention, is tension is positive, compression is negative. This is your direction coordinate system, and then the clockwise couple, for sigma xy, the shear stress, if it produces clockwise couple, anti-clockwise couple, which is taken as positive. But as I said, please put a star mark here. When we come to the strain different deformation mode, this sign convention will be clear. So this is for the timing, you take this sign convention for granted. Okay. So now, following the same concept, the previous, so this is the graphical representation of the stress at a given point in 3 dimension. We have how many components of stresses we have? We have total 9 components of stresses, 3 normal stresses and then 6 shear stresses, 2 on each plane, total 9 components. But again, if we apply the symmetry, the moment equilibrium, we can show that the shear stresses are same, sigma xy and sigma yx, they are same. So essentially, then we can have 3 normal stress and 3 normal stresses and 3 shear stresses, total 6 stress components. Now, these stress components are written in this form. So first is normal stress sigma xx, and then sigma y and sigma z. So these are 3 normal stresses. Then we have sigma xy, sigma yz and sigma zx. But remember, sigma xy is equal to sigma yx is equal to sigma zy and is equal to sigma xz. So the symmetry and all will be discussed in detail in next 2 weeks. There we will see that there are in addition to this, there are, depending on the material, there are many other kinds of symmetry exist. So this is in a vector form. Now if I have to express this in a matrix form, this sigma becomes, so this is sigma xx, then sigma xy and then sigma xz, sigma yx, sigma yy, sigma yz, sigma zx, sigma zy and sigma zz. Okay. So this is sigma written in, this is the stress written in matrix form. Usually when you when you see any book, there are 2 things you can observe. One is whenever we write tensor, second order tensor, then it is always written with a bold letter. Okay. So when it is sigma is written in a bold letter, it is not possible here, but if you see book, if it is written in a bold letter, implicitly you can assume it is written in a tensorial form. Okay. Another important thing is in book you will find in some of the book, instead of sigma xy, it is written as all the shear components are written as tau. So normal components are sigma x, sigma yy and sigma zz, but the shear components, instead of sigma xy, it is written tau xy, instead of sigma yz, it is written tau yz. They are not exactly same, but what is the difference? What is the difference between sigma xx notation and tau xy notation? Again, we will discuss next class when we define different kinds of strain, especially the shear strain. Okay. So if we apply this symmetry, so if we apply this, then this matrix is also become symmetric. And how many components we have here? We have total 6 component of stresses, 3 normal stress and 3 shear stresses. So this is how stress at a point can be represented. Okay. Now let us try to understand. There are some of the properties this stress tensor has. Okay. These properties are important, and what are those properties? But before coming to that property, you see, if you recall that if we have a coordinate axis like this, if you have a coordinate axis like this, and x, y and z, and then which is written as say O, x, y, z. Okay, this is the origin O. And then if you have another coordinate axis, for instance, here itself if we can write, this is say this is x dash, this is y dash, and this is z dash. Okay, and which is written as O, x dash, y dash, z dash. So if something is defined with respect to x, y, z coordinate system, x, y, z coordinate system means O, this coordinate system, and then the same thing when we define with respect to another coordinate system, the prime coordinate system. So we can transfer the we can have a transformation, we can define a transformation matrix which transform any quantity, any tensor, any order of tensor from one coordinate system to another coordinate system, right. So if we have, for instance, if we have stress, say sigma is the stress which is defined in this coordinate system, and sigma dash which is the stress with prime which is defined with respect to the prime coordinate system. Then sigma dash, if you remember, the sigma dash can be represented as q sigma q transpose, where q is the transformation matrix. Okay, and q, this transformation has certain properties, and the properties is q transpose is equal to y. So this transformation is orthogonal transformation. Okay, now if I same thing, if I write in initial notation, it says that q I j and q kj that's become delta I k, where delta is the Kronecker delta. So this is written, this property is the orthogonal property, the same thing written in indicial form as this. Okay. Similarly, if I have to write this transformation in indicial form, this will be that sigma I j dash, the ij component of tensor sigma dash, that will be equal to q I p. Please verify this, don't take this for granted. Q I q and then sigma p q, right, sigma p q. Okay. Now this becomes, this is j. Okay. So this is your this is written in initial form, right. Now why we are talking about transformation here? You see, there are certain properties, for instance, in this case, when we write sigma as this, when we write sigma is this, okay, the stress at a given point is this. What does it mean? It means that stress at a given point expressed with respect to this coordinate system, with respect to this coordinate system. But if I change the coordinate system, then what will happen? Then this stress, the representation of the stress with respect to a different coordinate system, still it can be represented it can be represented in a tensorial, in a tensor form, but the components of this tensor will be different, because the reference frame, the reference axis with respect to which these components are calculated, that is now different. Okay. Now, so it is very important when we say that stress at a point is this, or stress at a point either graphically or in a tensor form. When you write stress at a point, it is very important to mention that stress is represented with respect to which coordinate. If you change the coordinate, that representation will be, the components of that tensor will be different. Now, there are certain properties where which do not change if you change your coordinate system. For instance, if I say that say volume of this object, okay. Now, whether I take this as coordinate system or this as coordinate system or this as coordinate system, the volume of this object will remain same, isn't it? So, the volume does not vary. If we vary the coordinate system, the volume remain unchanged. So, this property is called invariant. This property means something which remain unchanged even if you change the coordinate system. Okay. Now, what we have seen here, if we change the coordinate system, then the representation of the stress, the components wise, everything will change. Okay. But there are certain properties in this stress tensor which remain unchanged even if we change the coordinate system, and those properties, those are called stress invariant. The invariant of stress tensor, there are three invariant of stress tensor. But before coming to that point, what are the three invariants of stress tensor? Let us suppose we know that consider the trace of this stress tensor. Okay. What is the trace of sigma? The trace of sigma is equal to sigma xx plus sigma yy plus sigma zz, right. Now, if I write that trace in initial notation, then the stress become sigma I, sigma ii. Ii is the repetition. So, as per Einstein convention, this is summation. So, it means sigma 1 1 plus sigma 2 2, sigma 3 3, or sigma xx plus sigma yy plus sigma zz. So, the trace of a matrix can be written in initial form is this. You are aware of this. Okay. Now, let us see what happened. By intuition, we can say that if we change the coordinate system, the components will change. Okay. But let us see what happens to the trace of this stress tensor, whether they change or they remain same. Okay. Now, to do this, let us write this is initial form of the transformation. Okay. Now, then with this initial form, if I sigma I dash, which is the trace of the stress tensor written with respect to prime coordinate system, this will be q I p q, j will become I here, because this is instead of j we are using I. So, this become I, then q delta p q. Now, look at this property, this is the orthogonal property. If q I j and q k j, it becomes delta I k. So, I p and q I q, this become q, so this becomes delta p q. Delta p q, this is sigma, delta p q into sigma p q. Okay. Now, what is delta p q? Delta p q is the Kronecker delta. This is 1 when p is equal to q, and this is 0 when p not equal to q. And then, so only if we take the non-zero term, other terms will be 0. There it is p is repeating and the q is repeating, means it will be summation over p and summation over q. P takes value 1, 2, 3 or x, y, z, q takes value 1, 2, 3 or x, y, z. So, similarly, we have many components here, but all will not be non-zero, only non-zero will be when p is equal to q, means it will be sigma 1 1 plus sigma 2 2 plus sigma 3 3 or sigma x x plus sigma y y plus sigma z z, which can be written in initial form as sigma p p. Okay, when p is equal to q. You see, so this is what? This is trace of trace of sigma, isn't it? And what is this? This is equal to trace of sigma prime, right. So, even the stress tensor, the component wise, they are different now with when they are expressed in different coordinate system, but if we take trace, the trace of sigma with respect to x, y, z this coordinate system and the trace of sigma with respect to this coordinate system, they are same. Means if we change the coordinate system, the trace of stress tensor does not change, it remain same. So, this is an invariant. Okay. So, this is the first invariant of stress tensor, which is written as I1. The first invariant is sigma or I written in indicial form, or trace of sigma is the first invariant. Okay. Similarly, other two invariants are I2. The second invariants are the cofactor, the sum of cofactor of this matrix. What are the sum of cofactor? If we check, the sum of cofactor will be in this case. So, if you take first this cofactor, if we take this, then cofactor will be, if you write it here, then this will be right sigma xx, sigma xy, and then sigma yx, sigma yy. So, determinant of this, plus another will be, take this sigma yy and then sigma yz, sigma zy and sigma zz. So, another one is this, and last one is plus. If you take the first and third row and first and third column, this will be sigma xx and sigma xz, sigma zx and sigma zz. So, this is sum of cofactor. You check that and you will see that sum of the cofactors of sigma is also an invariant. Okay. Now, this can be written in indicial form as this: half of sigma I sigma j minus sigma ij sigma I j, or sigma ji, since it is symmetric, that is why you can write sigma ij sigma ij. This is the second invariant of stress matrix. The third invariant is I3 will be the determinant of sigma. Okay. Now, determinant can be also written in terms of initial notation, as if you recall, the determinant of any matrix, suppose if any matrix is A, is determinant is written in terms of initial notation as epsilon I j k, epsilon I j k, which is the permutation sigma 1 I, sigma 2 k, 2 j and sigma, or sorry, A in this case, A and A 3 k. So, this is how you can write the determinant of any matrix. So, this is 3 invariant. What are the physical interpretation of these 3 invariants? We will discuss. Okay. Now, what we have done so far is, we have seen how to represent stress at a point in 2 dimension as well as in 3 dimension. We also have seen in 2 dimension there are 4 components of, we also discussed what are the sign convention and how these stresses are written, what are the meaning of when we write sigma xy, sigma yx, sigma yz and so on. We also discussed that for 2 dimension there are 4 component of stress, 2 normal stress and 2 shear stress, but 2 shear stress are same, which can be shown from the equilibrium, moment equilibrium. So, essentially there are 3 component of stress, and similarly in 3 dimension there are 6 component of stress. Then this stress can be written in a graphical form or in a vector form or in a matrix form. Okay. And if you, or in a tensor form. If you write in a tensor form, then in a 3 dimensional space, the stress is essentially a 2 or the second order tensor. Okay. Now, this second order tensor, the stress has certain invariant. Invariant means if you change the coordinate system, then the component wise the stresses will be different, but there are certain combination of these components which remain same, and these combinations are called stress invariant. There are three such combinations. The first one is the trace of the stress tensor, second one is the sum of cofactor, and third one is the determinant of stress. So, these are three invariant. Those invariants can be written in initial form as well. We stop here today. What we do in the next class is next class we will continue this discussion on stress and then see how to compute traction at a point, what is the meaning of traction, whether the traction at a point is again a valid word or not, what is the difference between stress at a point and the traction at a point. And then we will move on to define strain, different strain components, and then we also discuss when we write the strain components, we will discuss the another sign convention that I ask you to put a star mark, the sign convention for the shear stress. Okay. So, I will stop here today. See you in the next class. Thank you.